Well, I chose my presentation on the basic linear power supplies and voltage regulation, which is lab 5 of this class. My partner Gabriela Salinas helped out, and my name is Junior Pratas. Today's date is December 5th. And here we go. So basically, here's a basic outline of the presentation that I'm going to do. It's 3 parts: the introduction, the whole experiment, and results with conclusions at the end. And at the end, I'm going to have this slide again so we can talk about if you have any questions on these topics. Basically, at the beginning, we're going to have a line voltage right here, which is basically the wall power, 120 volts. We're going to put it into a step-down transformer, which is 10 to 1 or 1/10, however you want to look at it. That's going to bring us down to 12 volts, which we will inject into a full bridge rectifier. That rectifier is going to go into a regulator, and that regulated voltage is going to go into a load, and that's going to be the entire experiment. From then, we're going to go to a list of parts that we need. First of all, we need a power supply to make a power supply, picture to the side. We will need a multimeter, oscilloscope, power transformer, such as the one I mentioned earlier, 4 diodes for the rectifier, capacitors, various capacitors because we kept messing up our calculations, resistors for the dividers that I'm going to talk about later, power resistors to measure loads, various wire, but most importantly, we will need a little bit of fearlessness because we will be dealing with high voltages. So before the experiment, we ran a few calculations on every single possible transformer that we were given on the lab handout. With these 3 right here, the full wave, the dual outputs, we would have needed a negative ripple, like the ripple would have had to supply voltage to the rectifier, which wasn't possible, so we threw those out. And then we did the calculations for the half wave, full wave, and the voltage doubler. I believe we were not supposed to use the voltage doubler. So it was between the half wave and the full wave, which this is a big capacitor, so we ended up going with this one, and not just because Dr. Foltz forced us to. For the 3-terminal regulator, we have some input voltages. It's a little 7805 regulator. We have input voltages and output voltages. They start rising over here around 3 volts where the internal MOSFETs are going to start turning on. And then it starts to like linearly increase up until a peak of about 4.97 volts at an input of 6.5. So that's basically the voltage that we need. We need like higher than 5 volts output for this 3-terminal regulator. With a little bit of hacking, well, first of all, we added some loads to the 3-terminal regulator. We got some desired currents. We got some nominal resistor values for the currents, and we put those through the actual regulator to see if it was going to be good enough with the input voltage of 7.5 volts, which is 1 more than the cutoff voltage. And the efficiency, I threw it in there, and just to note that it was a very poor efficiency overall because it's an analog circuit, and it's not designed to be excellent. And with a little bit of hacking here, we can actually turn that 5-volt regulator into a 9-volt regulator through a little bit of clever math here, making this into a little voltage divider here. There is a 5 volts between the output and the common, which is what the regulator is supposed to do. But then after this divider here, we get an output of 9 volts at the end, and this is the bench power supply where we're testing the regulator first before we put it into our power supply. And as a 9-volt regulator, we ended up getting a voltage of 10.5 to get an output of 9.1, which is decent enough. But now for the unregulated power supply portion, that's the one that we used, the very pretty plywood one. We need to take a few things into account. Mains electricity can kill. We will need around 10.5 volts as our input, so we can get a steady 9 volts. We are using a center tap transformer here, but if we only use the left tap, we can make it into 12 volts because 24 volts would have been too much voltage to inject into the regulator. And we try not to become a victim of natural selection today. So, this is a diagram of the transformer we were given. If you ignore this bottom part of the center tap, it essentially becomes just a regular 120 to 12 volt transformer, which for the rest of this presentation we will be using the diagram on the right, so as to not create confusion. So now that when we have an unregulated power supply, we can add a full bridge rectifier here, a capacitor to create the the ripple instead of huge pulses. And a bleed resistor here for safety, so that if we ever left the circuit alone for too long, we don't have to worry about that capacitor remain charged for too long and risk somebody touching it and shocking themselves. So we did a few measurements on the unregulated power supply. We at no load, there was no ripple because the capacitor remained charged at all times. 33% load, the ripple got decently big, and at a full load of approximately 549 milliamps, we were assigned 600 milliamps. The ripple got pretty big, but apparently it wasn't too big because it was still above 9 volts, above 10.5 volts. And when we connected it to a variac, we got from 105 to 125 with a regulation of 10.7 to 1.7%. The ripples were pretty cool there, not too much, not too little. But I believe these are open voltages, so maybe that's why there wasn't too much of a ripple. So now we have our unregulated power supply here to the left, and over here we have a voltage regulator on the right. So when we put them together, you get a regulated power supply, which is what the entire purpose of this lab. That when we do not put a load to it, there is no ripple again because the capacitor is fully charged. The output voltage stays at a steady 9.33. We had a big load of 51 ohms. The output voltage is still decently staying strong at 932 with a ripple that's tiny. However, when we reduce the load to 16.24, trying to get that 600 milliamps, the output voltage dropped a little, and that's the reason for the load regulation being so big and the ripple being so huge. Unfortunately, that's not what we were expecting or hoping for, but we were too deep into to start changing numbers. We also connected it to a variac, and the regulator output stayed pretty strong, close to 932. Surprisingly, I wasn't expecting it to stay so close to 932 at 125, but it did, so that's good. Results. Mostly favorable, except for that last bit at the end. The voltage regulator did drop 1 whole volt at the full load, which again, that's not what we were hoping for, but again, it's just a lab and we're experimenting with analog circuits. And I would in the future, if I had to, use this as a DIY power supply and this whole circuit build. Conclusion, this lab is important to understanding analog circuits, of course. We're not going to start building switch mode power supplies in Junior Lab 1, even though those would be better. Switch mode power supplies are more efficient, more modern. We use them with nearly everything. I hardly believe we use any transformers nowadays, as much as we did maybe back in the 80s or 90s. And do not leave people alone with a variac because we will start shocking each other for fun. Any questions? For convenience, I made these into links so we can go back to any of these slides. Any questions?
Well, let me start. I'm going to have a quick comment in the 3-terminal resistor in the figure. You were displaying the graph about when you were measuring the voltage. Can you go to the 3-terminal resistor? 3-terminal resistor.
3-terminal regulator here?
Yeah, the very beginning. Yeah, there. Just as a comment, typically, if you're going to highlight a specific data point, make sure to add parentheses because that's how you would know them. Because otherwise, the audience might be thinking like, it's either 6.5 or 4 different values, right? Mm-hmm. Just to kind of as a general comment. Now, as far as my question, it's about the bleeder resistor that you have going on. I mean, I understand the purpose of it, right. But can you tell me what would happen if you were to increase that resistor to 10 mega ohms or 100 mega ohms?
It would generally take a little longer to discharge. It would be less in the way of the entire circuit, probably better if it's a more sensitive device. But for this purpose, 1 mega ohm is decent enough in my opinion for.
And if you lower it to 10K, for example,
it will definitely get in the way of the loads that we attach to it and the voltage regulator next to it.
Okay.
But it would be safer.
Thank you. Mm-hmm. That's all the questions I have.
How did you get C1? What was the value for C1 anyway?
I believe we had it set to measurements of transformers. Oh, it's in the beginning, right over here. We had it at 617 microfarads.
You actually had a 16. You
Well,
actually found a 617 microfarad.
We had a 570, and then we threw in a 100 one I believe we had laying around. So we went over that, but that's like the minimum requirement that we calculated.
Yeah, just a comment, a final schematic diagram should always have the component values on it. Just go ahead and put that. So, got a couple other questions, your parts list?
Okay. That's here.
Yeah. Anything missing there? Like maybe the most important part in the whole thing?
The voltage regulator.
Yeah, okay.
Right.
All right. Last question. Can we go to the results where you're showing the regulation for the unregulated supply?
Okay. Here.
That's regulated. Let's go to the, oh no, that's unregulated. Okay. So how do you define, on that bottom part you had line regulation? And line regulation is typically a single number and you got 3 different numbers there. How did you define line regulation?
For the Variac one?
Yeah,
Well, they told us on the handout that it was the change in voltage here with reference to the 115 volt voltage that we got. So from here, it would be this value minus this value divided by this value. And,
okay, yeah.
10.7%.
I mean, if you did it that way, the thing is, obviously it's an unregulated power supply and you're claiming it's 0%.
Oh, that's because it would be, this is the reference point right there. That's why
Okay,
we-
yeah,
we need it blank.
and by the way, that's why we don't do it that way. The way you would normally define it is the highest one
Oh.
minus it's the total variation divided by what it should have been.
Okay.
So you would take
Oh.
13.29 minus 11.66 and divide that by 13.07.
Okay.
Actually, I'll squeeze one more question in.
Right.
So on that next slide, the next one, the next one.
Okay. That's the regulator?
Okay, so as you pointed out that, at the highest load it failed, right?
Yeah.
So what could you change to get that to work again?
We could have tinkered with the regulator's voltage divider. We could have also had maybe a bigger capacitor.
Okay, so between those two, which would you say is the better option?
Probably the capacitor.
Yeah, and
Probably
why?
the cheapest component and less,
Actually, it's not the cheapest, it's way more expensive than the resistor,
oh, yeah.
but if you'd messed with the resistors, then your good values would also get messed up.
Right, yeah.
Okay, so the fact that you got the right output voltage with no load means your resistors are just fine.
Okay.
What you need to work on is the capacitor.